2, 1, welcome everyone to Math 266, Spring 2022. Alright, you are hearing the wonderful voice of me, your instructor, Professor Christopher Lee. There's my office, and there's my email. Alright, so let's start off things by just quickly going over the syllabus and what's this class about, what we're going to be doing, and then we'll talk a little bit more about the content of the course. All right, so first thing, the course is face-to-face, but as per my announcement, we had a previously standing doctor's appointment on Wednesday in Iowa City, so I cannot be there in person for this Wednesday, but I will see you on Friday in Gilman, 1652 at 9:55 a.m. So, see you in person then. All right, other information about the course, the text, hopefully you have acquired it in one way or the other. We will be using the online homework system that comes with this, so at the very least you need some sort of access code. If you want a physical copy of the book, great. Don't particularly need it, you can get the digital one. But yeah, so here is what we'll be talking about in the course. Hopefully, some of these words might be familiar. If they're not, that's okay. You may or may not have encountered eigenvalues before, but if not, we're going to learn all about it. All right, so briefly, what are we going to cover in the course? What's our goal? Well, we're going to learn all about differential equations, and in particular, we're going to cover the first 5 chapters out of the textbook, pretty much every section. A couple of them we're going to skip over, but, not too much. But anyway, here's just, by the end of the course, you'll understand all of this good stuff. There's basically 3 phases to the course. First order DEs, linear, higher order differential equations, and then systems of linear equations. All right, and in addition to the syllabus, which you can find on the Canvas page, which is, you must have found it because you found this video, there is also a calendar which gives a brief outline of when we're going to do everything in the class. So we are mildly coordinated here in DiffEQ. So everybody who's teaching 266 is more or less going to adhere to this schedule with some wiggle room here and there. So for example, homework number 1 was supposed to be due on the 20th. I pushed that back to the 23rd, the Sunday, because the first week of class with these online homeworks are always a disaster, so instead of having us do it Thursday, we'll just do that Sunday, but more or less we'll be hearing the schedule. This is also on Canvas if you want to look at it, but quizzes and exams will mostly stick to when those are going to go down. Alright, so speaking of homework, quizzes, and exams, let's talk grading. Your grade will be computed as follows. So the homework will account for 25%, the quizzes will account for 15%, the exams 36%, and the final 24%. Exams are worth 12, which is 3 of them, so that's why this is 36. And the final will be 24, twice as much as an exam. Yay. Alright, and the letter grades will be decided at the end of the semester, but with the following guarantee. So anything that's 87 or higher will give you the A-, 77, B-, 67, C-, so on and so forth with that. Yeah, pretty much. There you go. So let's talk about the other. So speaking of the assessments, let's talk about them. So again, as I already mentioned, the homework will be done online using my math lab, which we can access and should only access through Canvas. There are 2 tabs on the left, so there will be also a video explaining how our Canvas page works, so check that out. But basically, you can get to the homework through the immediate access course materials tab, which is where you can also get your textbook. But you can also get right to the homework via the assignments tab. And again, I'll have a video showing you how to do that, so check it out. Alright, so there will be 11 quizzes. They're going to be given on select Wednesdays. Check the calendar for which Wednesdays they'll be showing up. And as a general policy, calculators are not going to be allowed. All of the problems will be written so you can solve them without the use of calculators, so there won't be any weirdo numbers, and we're not going to ask for decimal solutions or anything. Everything can be done without a calculator. For homework, though, feel free to use calculator and Wolfram Alpha. You go nuts. But again, as assistants, not as a solver. All right, 3 exams will be given throughout the semester. Tentatively, they are set for those 4 dates. Note, none of those are the Friday before break. We're nice to you here in DiffyQ. And again, no calculators allowed. And any comprehensive final will be during finals week. Calculators, again, of any kind, not allowed. More information on when the final will take place and some more info on that when we get closer. All right, other things to talk about. So, general course policy thing. The Maps Department, we have a nice little list of policies we adhere to, which covers things like classroom behavior and also makeup policies. So if you have any questions about making up quizzes and exams, confer with that. If you have a acceptable exception for making up quizzes or exams, we will accommodate that. But again, check with an acceptable exception. You can't just be like, I overslept. Not allowed. But anything reasonable will work with you. Okay, then this paragraph is the chalk paragraph. The only reason we have to now include this in our syllabus. This is a university policy. This has to show up here because y'all couldn't behave with the chalk. All right, so there's that. Speaking of y'all can't behave, so regarding the continuing COVID-19 pandemic, check with the moving forward webpage for latest guidance from the university. So in class, I will be wearing a mask. I encourage you to do so as well. And that's the end of that. Alright, so that's it for the syllabus. If you have any questions about anything showing up here, again, best way to contact me is email. Office hours, I haven't quite figured out when those are going to happen just yet. They will probably be on Wednesdays and Fridays. I'm trying to avoid being on campus on Tuesday and Thursday. All my classes are on Monday, Wednesday, and Friday, so if I don't have to be on campus on Tuesday and Thursday, I don't want to be. But anyway. Alright. Alright, so that is a brief outline of the syllabus. Again, if you have any questions, email is the best way. Office hours, please come by once I get this figured out. Alright, so let's go back to the slides here. Day 1, Math 266. What up, yo? Alright, so before we get into the actual math stuff, a little bit more about me. So again, you will physically see me. This is what I look like right there. Here's my wonderful family. There's my wife Allison and our daughters Charlotte and Olivia. This photo shoot was great because Olivia was angry the entire time. This is like one of the better pictures of her. And Charlotte got a splinter in the middle of it, and she got very upset. So it was great. We got great pictures. This is like the best one. Alright, so again, before we end it, a little bit more about me. So as will become apparent as we go on the semester, I am from New York. I'm from Long Island. I'm specifically from somewhere called West Islip. I am of Italian descent, like everybody from Long Island. So, as we go on here, the accent will come out. Long Island. That'll be fun. Alright, so speaking of New York, which was really fun, I went to school in New York. I went to a school that no one's ever heard of called Clarkson University, which is in Potsdam, New York, which is right by the Canadian border. And I got all my degrees in mathematics from there. And it's a very special year this year because it's been 10 years since I got my PhD. So that's exciting. Alright, and in addition to mathematics, the other thing I waste all of my time on is chess. So, if you feel like playing, check it out on the Bad Chess website, or the good one. My name is the same on both of them, Bishop's Lemma, which is very convenient considering my PhD was based on the work of a mathematician named Eric Bishop. So I was pretty excited that nobody had taken this name yet, so that's what I got. Alright, cool. Alright, now, let's get to the actual course. Alright, so what are we going to be doing? Solving differential equations, which we will refer to as DiffyQs, or Ds, or as my best friend liked to write it, DiffyQs like that. So, yeah, that's our goal. We're going to solve differential equations. Alright, well, what is a differential equation? It's an equation with a derivative. No more, no less. That's it. So, here you go. Pretty classic example. Right here we've got an equation and there's a derivative. So dy dx is equal to 2y, or y prime is equal to 2y. So we'll write it in either form throughout the semester. And here y is representing an unknown function, and x is a independent variable. So x can do whatever it wants, but y is dependent on it. So y is a function dependent on x. Sometimes y is referred to as the dependent variable in this case. So we will use both notations, the prime notation and the Leibniz notation. Note in the prime notation, we are hiding what the independent variable is. So in situations like that, we can make the independent variable be whatever we want, but, you know. Now, something we want to get into the habit of, and hopefully you've gotten into this habit, but if not, is reading equations. So the differential equation y prime is equal to 2y, when you see that, you should read that as, I want to know the function whose derivative is twice itself. Right? And when you read it like that, the function whose derivative is twice itself, you immediately should think of an answer, which I already spoiled. Should have put a pause there. You should immediately think of e to the 2x, right? We know from calculus that the function whose derivative is itself is e to the x, and that uniquely determines e to the x, actually. More or less. More on that a little bit later. And if we want twice it, well, by chain rule, we know that if we throw in a 2x up here, the derivative will spit out twice the original function. So this is something I really want to stress, and I'll stress throughout the semester. We're going to write a lot of equations, and you really want to get in the habit of reading them. Because we will develop a lot of powerful techniques of solving differential equations, but when it comes to something like this, just read it. You know a function whose derivative is twice itself, e to the 2x. Alright, and getting the habit of reading it also will help us differentiate between the two. So note that these two differential equations are very similar, but there's a key difference between them. Dependent variable, independent variable. And now note, this one can be solved by just integrating both sides. The integral of y prime is y, and the integral of 2x is x squared. There's some constants that'll show up, but a little bit more on that later. Okay. Whereas this, if you tried to integrate it, this wouldn't solve it. You'd get y is equal to twice the integral of y, which, that's an integral equation, not a differential equation. Integral equations are a thing, but we're not going to talk about them. Okay, so getting in the habit of reading the equation, because if you read this, it says, find me the function so that its derivative is twice its input, x squared is an answer. Alright, so when it comes to differential equations, something we're going to be doing a lot is classifying them. So in other words, right, given a DE, is it of a particular form? Because there's probably some techniques that work for ones that don't work for others, and that'll be true as we go through the semester. So in this class, we're going to focus primarily on things that are called ordinary differential equations, also known as ODEs. And these are differential equations where there is only one independent variable. So y prime is equal to 2y is one that we will frequently see. The other type of DEs that are out there are partial differential equations where there are multiple independent variables, and instead of just plain derivatives, there are partial derivatives flying around. And these show up in a lot of places, but we will never speak of them. We will talk about partial derivatives a little bit, and if you've taken Calc 3, you know what they're all about. If you haven't taken Calc 3, don't worry, we'll do a quick crash course on them. And if you want to know more about these, and you should, because they're super cool, take Math 385 after you're done with this course. And also, speaking of taking more math classes, I am also the director of undergraduate studies here in the math department, and y'all probably engineers, let me tell you, you're like 2 math classes away from the minor and basically 4 away from a major. So if you're interested, talk to me and I'll hook you up. And you should take this class anyways. It's super cool. It's one of my favorite math classes I took as an undergrad. So, all right. So again, we'll focus on ODEs, one independent variable, but PDEs is some good stuff. All right. So the first thing we're always going to address when we're looking at a differential equation is figuring out what its order is. The order is the highest derivative that shows up in the equation. So, for example, a first order DE only has one derivative, and here you go, y prime is equal to 2y minus e to the x. That is a first order differential equation. The highest derivative I see is the first derivative. Here's one that's second order. The highest derivative I see is the second derivative. Beautiful. And now we want to be very careful here, because the next one I'm about to show you, you might see the cubing and go, ooh, third order. But no. That is cubing this function. That's not taking the third derivative of it. So this is still a first order dE, because the highest derivative I see is still the first one. Okay, so pay attention to notation. Again, read equations. I'm looking at a function whose derivative is the square root of 1 plus the cube of its derivative. So in this class we are going to solve these ones for sure. I'll briefly mention how you solve these, but that's more of a 267 thing. And straight up, I've got no idea how you solve this one. I don't even know if this could be solved. More on solving a DE in a moment. The other thing about a DE that we're going to care about is if it's linear or not. And broadly speaking, a linear DE is one where the only operations applied to the unknown function are addition and scaling by functions dependent on the independent variable. So for example, this equation is linear. The unknown function that we're interested in, y, it's being derivatived, it's being added, and that's it. So it's linear. Here, this is nonlinear because the unknown function is inside of tangent. This is linear because the only operations being applied to y are derivatives, addition, and scaling by functions dependent on the independent variable. Whereas this right here is nonlinear because now I'm squaring y prime. So another way of detecting linearity is, does it look like this? So here's the general form of an nth order linear DE. It's gross, right? This is, right, if I just showed you this is what it means to be linear, right? But the general rule of thumb is, if the only things happening to our unknown function are derivatives, addition, and scaling by functions that only involve the independent variable, then we're good. Now, if you're looking at this and you're going, hey, this kind of looks like, I don't know, a polynomial, right? If you think about this as powers and these as coefficients, oh, hey, this is just like a polynomial. Yeah. I wonder if there's some deep connection between those two that we're going to investigate later on in the course. Beats me. No idea. All right, so I've already kind of let it slip, but what does it actually mean to solve a DE? So solving a differential equation, well, let's consider this one right here. X times y prime plus y equals 0. So find me a function whose derivative times the independent variable plus the original function gives me 0. So I want a function that does that. So if I solved it, that means I've got a function satisfying that, but also, and this is something we're going to care a lot more about in the beginning of the semester and kind of not care about later on, you also need to give me a domain, and this particular DE really highlights that, because if we let phi be 1 over x, if you do x times the derivative of phi plus phi, you get 0. So phi of x here satisfies the DE. But we got to be a little bit careful. This is not defined for all real numbers. And since we're talking about derivatives, we really need our domains to be an interval. So in this case, we will say that the function 1 over x is a solution to the differential equation, so long as you force the domain values to only be strictly positive. You can make them strictly negative if you wanted to, but in most practical applications, the independent variable is time, and time usually may be positive. Okay, so this would be a solution. It satisfies the DE, and we've also determined a meaningful domain. So like I said, we'll care a little bit more about domains in the beginning of the course. As we go on, we're going to stop caring. But it is something to keep in mind, because when I say here's a solution, especially if you have something like this, where the function is not defined everywhere, you really got to tell me what inputs you care about. And a little later on, we'll talk about a phenomenon known as blow-up, where the domain is actually going to be finite. So that's going to be interesting. Well, we got there. But, so broadly speaking, what does it mean to solve a DE? You found a function satisfying the required equation. I have meaningful inputs to put into it. Now, in practice, we normally like a nice closed form for our function. We have an explicit explanation for it. It's 1 over x. But sometimes, we don't necessarily get that. So consider this. This is the following differential equation, but it's written in its differential form. So one of the benefits of the Leibniz notation, dy over dx, is that I can treat this like a fraction, multiply the dx over, and subtract it over, and get this form right here. And as we'll see when we talk about exact differential equations, sometimes it's better to be in your differential form than it is to be written like this. Now, for this particular DE, this expression gives me an implicit solution, because if I implicitly differentiate this, it will satisfy the DE. So take the implicit derivative of this, so multiply everything tree-wise function of x, do outer derivative rules, we'll get that. So this defines solutions. It doesn't give me a formula for them, but it gives me an expression that says any solution would have to satisfy this. Now, of course, you can add the x cubed over and take the square root, but again, meaningful domain. Once you take a square root of something, well, now you've got to make some decisions about what inputs are allowed. So that gets into, right, again, you got to be careful. So some situations, some DEs, we're just going to be happy with this and just move on and go, if you want an answer, it has to satisfy this. There are multiple functions with multiple domains flying around. You pick the ones you like, basically. All right, beautiful. Okay, so sometimes we'll get answers, but they won't be like, y equals 5e to the x. Sometimes they'll look like this. And sometimes they'll look even worse than this. Sometimes it'll straight up be an integral. It's the integral of this function. So some famous integrals that we can't handle, like the integral of e to the x squared, e to the x squared. We don't know, we don't have an equation for that. So sometimes it gets real bad and you just go, well, this integral works. But, all right. So something else about solutions, and hopefully you kind of caught it right here. 8 here didn't matter. 8 could have been whatever number you wanted. So our experience from calculus says that, well, if I'm solving a differential equation, that means I'm undoing a derivative. And as we learned, undoing derivatives, right, anti-differentiation, will introduce constants, right, because derivatives kill constants. So when I say y prime is equal to 2 to the x, find me a function whose derivative is twice itself, certainly e to the 2x works, but also any scalar multiple will also work, because if I take the derivative, we'll pick up the 2, but the constant will just go along for the ride and not care. So any solution will have to be of that form. So something like this we call a general solution, or in this case, a one-parameter family of solutions. Right? So this differential equation has not just one solution, but in fact infinitely many. And so that's one benefit of DFQs, that there's multiple answers. And multiple answers is always a good thing. No answers is the worst. Having multiple answers is great, because then you just pick which one you like. And in certain situations, we'll be able to pick our favorite ones. Specifically, the general solution to this is that, but if I'm further told that y of 0 is 6, well, I can plug that in. This is telling me that when x is 0, y needs to be 6. So 6 is what y is equal to. Plug in 0 for x. E to the 0 is 1. And so we solve that, and that tells me that the unique solution to this setup here, differential equation with some initial information, which is called an initial value problem, or an IVP, has a nice unique solution. Y is equal to 6 e to the 2x, and we are going to be doing a lot of these in this class. All right, so let's finish things off with a parting shot here today. Consider the following initial value problem. Y double prime minus y equals 0. Y of 0 is 1. Y prime of 0 is 3. All right, so if I want to solve this differential equation, well, first of all, it'd be great to figure out a general solution. So, as I noted, we will learn a general technique of solving these, but you can check that this right here is a general solution. Note, there are 2 functions and 2 unknowns. That hopefully is not shocking because there is 2 derivatives. All right. Now, take a derivative and a second derivative. Second derivative minus y, I need that to equal 0, and we see that indeed that happens. So this is a general solution. And then plugging in the initial conditions gives me, a system of equations, C1, C2, And here now, we can solve this. And if you've taken linear algebra before, you know that there's a nice systematic way of doing this using Gaussian elimination, or you can just brute force this by going, well, add these two. I'll get 4 is equal to 2 C1, so C1 needs to be 2, and then from there you can solve that C2 is negative 1, and thus we find that a unique solution is y is equal to 2e to the x minus e to the negative 2x. Beautiful. All right, so this is giving us a little future glimpse into some things we're going to be doing in this course. So we will learn how to actually solve these. We will spend some time learning about how matrices are going to help us solve things in this course. And something that you're hopefully noticing is, man, e to the x seems to be a solution a lot of the times. Well, it is its own derivative, so it's not too shocking that we're going to try to use that to solve things. But as you'll see, pretty much every DE gets solved by using e to the x in one way or the other. All right. Cool. All right, and that is it for day 1 for us. Okay, so again, I will see you all in person on Friday, where we will start making some actual steps in actually solving differential equations. So what are the actual techniques we need? This just kind of gave us a quick little overview of some of the stuff we will be doing, and giving us a little flavor for how things are going to go. So we'll start talking about the actual methods of solving on Friday. And I'll see you then. Yeah, that's it.